Hello. We are the Thermistors. My name is David Quintanilla.
And I'm Ryan.
And I'm Xavier.
For our group project, we did a Thermistor. Um, First up is going to be our Flash server hosted on the Raspberry Pi. It was a basic Flash server created using Python. Running off one of our previous labs, the Flash server was pretty easy to set up. What it did was imported serial data from the thermistor and displayed the graph on the server, and it updated about every 5 minutes. Next up is going to be the web server code. Written in Python, one of the biggest challenges I had was importing the API correctly. I wanted it to display the zip code, and it took a couple tries before, but we eventually got it. It imported the thermistor graph as well as the index HTML files, and which we created a template folder so it'd be a little easier to track. Next up will be the Open Weather Map API. Open Weather Map was a great API to use. If you're looking at Bulletin 1, that's the actual call for the API. It was able to display the temperature in any zip code in America. Next up, instead of displaying in Celsius, I displayed it in Fahrenheit, and it was a simple conversion in the code. And the air temperature was around plus or minus 3 degrees overall.
So one of the initial issues that we faced was the fact that most of the project actually relies on the Raspberry Pi, but one of its limitations is that it can only interpret digital input. So in order to interpret the analog input from the thermistor, it had to be first interpreted by the STM32 microcontroller, which is capable of reading analog signals. So using UART on the STM32, I was able to transfer data through a serial connection, which in this case was transferred through USB, so that I could then receive the now digital input on the Raspberry Pi. The digital serial input was handled using the Python serial library. So graphing the data, the thermistor input graphs were made by reading in input data from the UART serial connection. Every 6 seconds, a Python script will read in a line of data 10 times from that serial connection and then append it over to a CSV file. The CSV file is then read and then plotted using the Python library matplotlib. The plotted data then gets saved over as a PNG file and then saved into the static folder, which is where the web server expects it to be, so that I can then render it on the web page.
Next, we have the finite state machine wiring. The finite state machine consists of 4 resistors, a thermistor, a Raspberry Pi, and an STM32, as long as 3 LEDs. The resistors are needed for the LEDs and thermistor. The STM powers and grounds our thermistor. It then sends the temp collected by the thermistor to the Raspberry Pi. Our Pi then powers our LEDs and shows the current state indicated by those LEDs. With the temperature finite state machine, this has 3 states represented by green, yellow, and red LED. Each state is set to a specific range of temperatures, the green being an ideal temperature, yellow being less than ideal, and red being a temperature outside of our range. This FSM would be primarily ideal for a machine that needs to be powered off if it's outside of the ideal range. And then in conclusion, the thermistor we use, we found out wasn't really meant for our case. It does well for ambient room, or it did not do well for ambient room temperature, but we figured that's because it's best used for internal temperatures where the temps are kind of an extreme case. Also, after looking through the open weather maps, we found that it's a very good API once we got it properly sorted out. And then we also realized this project probably could have been ran strictly off the STM, but because we needed the Raspberry Pi, to do the host to server. We were going to have to go ahead and use them in unison to convert those signals. And that's all. Probably should have ended that. Oh.